The night sky is filled with millions of stars. Each of those stars is a sun, and our own sun is just one amongst billions in a swirling sea of galaxies. It's hard to believe, but even this grand show has to come to an end someday. Our sun will burn out. But what about the whole universe? Will it go out in a bang or fade away to nothing? Join us as we look for answers about the ultimate fate of everything. We'll delve into the mysteries of dark matter, dark energy, and the mysteries of black holes to understand what really controls the universe's story. How will everything end? Located within the sprawling cosmos, our planet Earth resides in a location that might seem modest at first glance, but is profoundly special upon closer examination. Orbiting a rather ordinary star we call the Sun, Earth is just one of 8 planets in the solar system, which itself is part of a much larger galaxy known as the Milky Way. This galaxy, with its spiraling arms, contains hundreds of billions of stars, many of which are likely home to their own planetary systems. The Milky Way is but one of countless galaxies in the universe, each with its own unique assortment of stars and planets, floating in the vastness of space. The Sun, around which our Earth and other planets revolve, is located in one of the Milky Way's spiral arms, known as the Orion Arm. It's about 26,000 light-years away from the galactic center, a bustling hub of intense cosmic activity where a supermassive black hole resides, influencing the galaxy's dynamics with its immense gravitational pull. Despite the incredible distances involved, the Milky Way is only our cosmic neighborhood in the much larger universe. Expanding our view beyond our galaxy, we find ourselves within a local group of galaxies that includes not only the Milky Way, but also Andromeda, our nearest galactic neighbor, and about 54 other smaller galaxies. This group is part of the Virgo supercluster, which is itself only a small component of the Laniakea supercluster, a colossal structure that spans over 500 million light-years and includes hundreds of thousands of galaxies. In the fascinating thought experiment where we compress the universe's 13.8 billion year history into the span of a single year, known as the cosmic calendar, our perspective on time undergoes a dramatic transformation. In this calendar, each second represents about 437 years, allowing us to visualize the vast timeline of the cosmos in a more comprehensible way. January 1st marks the Big Bang, the universe's explosive birth, setting in motion the cosmic saga that leads to the present moment, symbolically at midnight on December 31st. As the cosmic year unfolds, the earliest months are dominated by the formation of fundamental particles and atoms, with the first stars igniting in the universe's dark expanses by the end of January. Galaxies begin to form in March, spinning and gathering in the vast cosmic dance that structures the universe. Our own Milky Way galaxy takes shape around May, setting the stage for the eventual emergence of our solar system. The solar system's formation kicks off in August, with the Sun and its planets coalescing from a cloud of gas and dust. Earth forms shortly thereafter, but it is not until September that it cools enough for a stable crust to form and for the earliest forms of life to appear. These initial life forms are simple, microscopic organisms, but their existence marks a significant milestone in the cosmic calendar. Fast forward to December, and the pace of events quickens. Complex life begins to emerge and diversify in the oceans. By December 17th, the first land plants appear, followed by the dinosaurs' reign, which dominates the landscape until their sudden disappearance around December 26th. This paves the way for mammals to rise and diversify, leading to the first hominids stepping onto the scene in the final moments of December 31st. The entirety of human history, from the development of agriculture to the construction of the pyramids, from the Renaissance to the digital age, unfolds in the last few seconds of the cosmic year. It's a humbling perspective that highlights the brevity of human existence in contrast to the vast, ancient expanse of the universe. The Big Bang Theory stands as a monumental explanation for the origin of our universe, proposing that everything began from a singular, infinitely dense point approximately 13.8 billion years ago. This initial explosion set the universe on an expansive course, which continues to this day. The evidence supporting this theory is both profound and multifaceted, painting a picture of the universe's earliest moments and its subsequent evolution. One of the most compelling pieces of evidence for the Big Bang comes from the observation of the cosmic microwave background radiation. This is the afterglow of the initial explosion, a faint cosmic whisper that fills the entire universe. Discovered by accident in 1964 by Arno Penzias and Robert Wilson, the CMB is a nearly uniform background of microwave radiation that is detectable in every direction we look. Its discovery provided a significant boost to the Big Bang Theory because it was exactly what would be expected if the universe had started in a hot, dense state. The CMB's uniformity, with slight variations or ripples, also gives scientists crucial insights into the distribution of matter in the early universe, leading to the formation of galaxies and other large structures. Another pillar supporting the Big Bang Theory is the observation of the universe's expansion. In the 1920s, Edwin Hubble made the groundbreaking discovery that galaxies are moving away from us, and further away, galaxies are moving faster. This observation, which can be likened to dots on an inflating balloon moving apart from each other, indicates that the universe is expanding. The logical extrapolation from this observation is that if the universe is expanding now, it must have been smaller and denser in the past, ultimately converging to a singular point from which it began to expand. The abundance of light elements, specifically hydrogen, helium, and lithium, in the universe also supports the Big Bang Theory. Predictions based on the theory suggest that in the hot, dense early universe, conditions were ripe for the formation of these light elements in just the right proportions observed today. The fact that the observed abundances of these elements throughout the cosmos align closely with theoretical predictions from the Big Bang nucleosynthesis provides a strong empirical foundation for the theory. These pieces of evidence, the cosmic microwave background radiation, the observation of the universe's expansion, and the abundance of light elements, form a coherent and compelling case for the Big Bang as the origin of our universe. Embarking on a journey through the life cycle of a star, particularly one akin to our Sun, unveils a narrative of cosmic transformation and evolution that stretches over billions of years. This story begins in the cold, dark nurseries of space known as molecular clouds, dense regions filled with gas and dust. Within these clouds, pockets of gas gradually accumulate under gravity's inexorable pull, eventually reaching densities and temperatures sufficient to ignite nuclear fusion in their cores. This moment of ignition marks the birth of a star, entering what is known as the main sequence phase of its life. During this main sequence period, a star like the Sun fuses hydrogen into helium in its core, releasing enormous amounts of energy. This process, which for our Sun will last about 10 billion years, is remarkably stable, balancing the inward pull of gravity with the outward pressure of nuclear fusion. The light and warmth that our Sun has provided for some 4.6 billion years, and will continue to provide for about another 5 billion years, sustains life on Earth and governs the rhythms of our planetary system. As the star exhausts its hydrogen fuel, the story takes a dramatic turn. The core contracts and heats up, while the outer layers expand and cool, transforming the star into a red giant. This phase sees the star's diameter swell to many times its original size. If this were to happen to the Sun, it would engulf the inner planets, including Earth. In the heart of the red giant, helium now becomes the fuel, fusing into heavier elements like carbon and oxygen. For stars of mass comparable to the Sun's, this stage leads to the shedding of their outer layers, creating a beautifully colored cloud of gas known as a planetary nebula. What remains is the core, a white dwarf, a dense, dim remnant about the size of Earth, but with a mass near the Sun's. This white dwarf will gradually cool and fade over trillions of years, ending the star's life cycle as a cold, dark, and dense object. As our Sun embarks on its inevitable journey towards becoming a red giant, the transformation will have profound and far-reaching effects on the planets of our solar system. This metamorphosis, marked by the Sun's dramatic increase in size and decrease in surface temperature, will unfold over billions of years, but its impact on the planetary bodies orbiting the Sun will be both stark and varied. The inner planets, including Mercury and Venus, will face the most immediate and catastrophic consequences. As the Sun expands, it is expected to engulf these planets completely, effectively vaporizing them due to the intense heat and gravitational forces at play. Earth's fate, while uncertain, hangs in a delicate balance. It may narrowly escape being swallowed, but will nonetheless suffer extreme heating. This intense increase in temperature could strip away the planet's atmosphere and evaporate its oceans, rendering it uninhabitable and barren. Mars, a bit further from the Sun, will also experience significant changes. The increased solar luminosity will warm the Martian surface, potentially making it more amenable to atmospheric retention and perhaps even liquid water on its surface once again. However, this would be a temporary phase, as the Sun's continued evolution and eventual shedding of its outer layers would lead to a decrease in solar luminosity and an increase in the distance to the remaining planets. The outer gas giants, Jupiter, Saturn, Uranus, and Neptune, will witness a different kind of transformation. The increase in solar radiation could alter their atmospheres, possibly stripping away some of the lighter elements and changing their appearance and composition. Their moons, many of which are considered potential candidates for harboring life, could see their ice-covered surfaces melt, leading to temporary liquid water environments that might support life for a brief period. As the Sun loses mass during its red giant phase, the gravitational hold on its planets will weaken, causing their orbits to expand and move further away. This shift could lead to significant changes in the dynamics of the solar system, including orbital resonances and the potential ejection or destabilization of comets and asteroids in the Kuiper Belt and Oort cloud, sending them on new trajectories through the solar system. In the aftermath, with the Sun reduced to a white dwarf, the remaining planets will orbit a much dimmer, less massive star. The solar system will be a vastly different place, with any surviving planets receiving only a fraction of the light and warmth they once did. This new, colder solar system will be a quiet testament to the Sun's once vibrant past. The death of a Sun-like star is not an end, but a breathtaking transformation, giving rise to one of the most beautiful phenomena known to astronomy, the planetary nebula. As a star exhausts its nuclear fuel and sheds its outer layers, it crafts a stunning spectacle of light and color, a celestial masterpiece that can illuminate the cosmos for thousands of years. This process, a consequence of the star's evolution beyond the red giant phase, reveals the intricacies of stellar life cycles and the creation of new structures from the remnants of stellar death. When a Sun-like star enters the final stages of its life, it begins to lose its outer layers into space, propelled by intense stellar winds. What remains at the core is a hot, dense white dwarf, emitting strong ultraviolet radiation. This radiation illuminates the expelled gas, causing it to glow in a kaleidoscope of colors. The intricate shapes and patterns of planetary nebulae, ranging from rings, shells, and spiral structures to complex, irregular forms, are the result of interactions between the stellar wind, magnetic fields, and the interstellar medium. The name planetary nebula is a misnomer, stemming from their early telescope observations as round, planet-like disks, but they are, in fact, vast clouds of ionized gas surrounding the remnants of dying stars. Each planetary nebula is unique, displaying a variety of colors based on the gases present and the temperatures achieved, are just a few examples of the diverse and enchanting forms these nebulae can take, each a testament to the complex processes at work in the depths of stellar interiors. The formation of planetary nebulae marks a crucial phase in the recycling of cosmic material. The elements forged in the cores of stars and expelled into space become the building blocks for new stars, planets, and possibly life itself. In this way, the death of a star enriches the cosmic environment, contributing to the ongoing cycle of stellar birth and death that drives the evolution of the universe. Dark matter, a mysterious and invisible substance, plays a crucial role in the cosmic ballet that shapes the universe. Though it emits no light and cannot be seen directly with telescopes, dark matter's presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Comprising about 27% of the universe's mass energy content, dark matter far outweighs the ordinary matter that makes up stars, planets, and all living things. The concept of dark matter emerged from the observation of galaxies and galaxy clusters that did not behave according to the laws of gravity as we understood them. In the 1930s, astronomer Fritz Zwicky noticed that galaxies within clusters moved so fast that they should have flown apart if only visible matter were holding them together. Similarly, in the 1970s, Vera Rubin and Kent Ford observed that stars at the edges of galaxies orbited at the same speed as those near the center, defying expectations that their speeds would decrease with distance from the galactic core. These and other observations suggested the presence of an unseen mass exerting additional gravitational force, leading to the dark matter hypothesis. Dark matter's gravitational pull is essential for understanding the formation and evolution of cosmic structures. In the early universe, slight fluctuations in the density of matter provided the seeds around which galaxies formed and grew. Dark matter, with its invisible scaffolding, amplified these initial irregularities, attracting ordinary matter through its gravitational pull. This process led to the formation of stars, galaxies, and galaxy clusters, sculpting the universe's vast web-like structure. While dark matter's gravity helps to shape the cosmos, its interaction with the universe's expansion offers insight into the nature of space itself. The universe has been expanding since the Big Bang, with galaxies moving away from each other over time. Dark matter's gravitational influence works against this expansion, slowing it down. However, this deceleration is counteracted by dark energy, a mysterious force that is driving the universe to expand at an accelerating rate. The interplay between dark matter and dark energy is a central theme in cosmology, as scientists seek to understand how the universe can simultaneously hold together at the large scale while also pulling itself apart. The discovery of dark energy emerged from observations of distant supernovae in the late 1990s. These observations revealed that the universe was not just expanding, but that the rate of expansion was accelerating. This acceleration was unexpected. According to conventional understanding, gravity should have been slowing down the expansion. The force responsible for this acceleration, later termed dark energy, suggested that the fabric of the universe is filled with a constant energy density that pushes space itself apart. The precise nature of dark energy remains a puzzle. One leading theory suggests it could be a property of space itself, described by Albert Einstein's cosmological constant, a term he introduced in his equations of general relativity. According to this idea, Empty space is not truly empty, but has its own energy. As the universe expands, new space forms, and with it comes more of this energy, fueling further expansion. Another hypothesis posits that dark energy is a dynamic field, similar to electromagnetic fields, varying over time and space. This concept leads to models where the strength of dark energy can change, influencing the rate of cosmic expansion in different ways at different times. However, no direct evidence for such a field has been found, leaving its existence in the realm of theoretical speculation. The fate of the universe, a subject of intense speculation and scientific study, hinges on the battle between the forces of expansion and contraction. This cosmic tug-of-war, influenced by dark energy, dark matter, and the overall mass and energy content of the universe, leads to several possible outcomes for its ultimate fate. The question of whether the universe will expand forever or eventually collapse back on itself is central to our understanding of cosmology and the nature of the cosmos. Current observations and theoretical models suggest that the universe is not only expanding, but doing so at an accelerating rate. This acceleration is attributed to the mysterious force known as dark energy, which appears to dominate the universe's energy content. The repulsive force of dark energy works against the gravitational pull of matter, including the dark matter that binds galaxies together. As dark energy propels the expansion of the universe, it leads scientists to the prevailing view that the universe will continue to expand indefinitely. The heat-death scenario of the universe, often considered in the context of its ultimate fate, is a concept that hinges on the principles of thermodynamics, particularly the second law, which states that the entropy of an isolated system will always increase over time. In the cosmic scale, this translates to a future where the universe has reached a state of maximum entropy, a point at which all energy is evenly distributed, and there are no gradients left to drive processes that can convert energy into work. This state is often described as the universe's final act, marking the cessation of all astronomical and physical activity in a cold, dark, and lifeless cosmos. In this scenario, the universe would continue to expand, driven by dark energy, spreading matter and energy thinner and thinner across the vastness of space. Over trillions of years, stars would exhaust their nuclear fuel, galaxies would cease to form new stars, and existing celestial bodies would either collapse into black holes or fade away as their light disperses into the expanding universe. As black holes themselves slowly evaporate through Hawking radiation, a quantum mechanical process predicted by Stephen Hawking, the universe would be left with a sparse soup of particles and radiation, evenly spread across an ever-expanding space. The heat-death scenario posits a universe where all processes that increase entropy have run their course, leaving behind a state of thermal equilibrium. In this equilibrium, temperatures across the universe would approach absolute zero, where no further energy exchanges are possible because everywhere is at the same temperature. The lack of temperature differences, and therefore energy flows, means that no work can be done, and the universe would become static, devoid of change, and unable to sustain any form of life or movement. This depiction of the universe's end is based on our current understanding of physical laws and the observed acceleration of cosmic expansion. It suggests a slow, inexorable slide into a uniform state, rather than a dramatic conclusion. While it might seem bleak, the heat death of the universe is an event so far in the future that it defies human comprehension of time, occurring over time scales many orders of magnitude longer than the current age of the universe. The Big Rip theory presents a dramatic and cataclysmic model for the end of the universe, distinct from the gradual chill of the heat death scenario. This theory hinges on the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. If dark energy's repulsive force increases over time, it could eventually overpower the gravitational forces holding galaxies, stars, planets, and eventually atoms together. The Big Rip theorizes a finale where the fabric of the universe itself is torn apart, leading to a universe that is quite literally ripped to shreds. The premise of the Big Rip is based on a particular form of dark energy with a density that grows without bound. In such a universe, the expansion rate not only accelerates but does so at an ever-increasing pace. This scenario leads to a future where, at a certain point, the expansion becomes so rapid and overpowering that it begins to overcome all forms of gravitational and electromagnetic binding forces. In the timeline leading up to the Big Rip, galaxies would first be separated from each other as the space between them expands more quickly. Following this, gravitational forces within individual galaxies would weaken, causing them to disintegrate. Solar systems, including our own, would lose their cohesion next, with planets being flung into the darkening void as the bonds that tether them to their stars are severed. As the final moments approach, stars, planets, and even molecules would disintegrate, as the repulsive force of dark energy overcomes the forces that bind atoms together. In the last instance, atoms themselves would be torn apart, with the very fabric of space-time succumbing to the relentless expansion, leaving behind a universe devoid of any structure, filled with isolated particles rushing away from each other. The Big Rip represents one of several speculative but theoretically plausible outcomes for the universe, contingent on the precise nature of dark energy. If dark energy's strength grows over time, then the Big Rip becomes a possible end scenario. However, if dark energy remains constant, as in the cosmological constant model proposed by Einstein, or if its strength diminishes, the universe may follow a different path, such as eternal expansion or eventual collapse. The Big Crunch is a theoretical scenario for the universe's end, where, instead of expanding indefinitely, the cosmos reverses its course and begins to contract, ultimately collapsing in on itself. This fascinating yet daunting concept stems from the idea that if the total density of matter and energy in the universe is high enough to overcome the expansion driven by dark energy, gravitational forces will eventually win, pulling everything back to a singular point of infinite density. In this scenario, the universe's grand expansion, witnessed since the Big Bang, gradually slows down as the collective gravity of all cosmic matter and dark matter begins to halt the outward flight of galaxies. Once this expansion stops, the contraction phase begins. The process would not be instantaneous, but would unfold over billions of years, mirroring the universe's initial expansion, but in reverse. As the contraction accelerates, galaxies would start moving closer together. This would mark a dramatic shift from the current state of cosmic drift, leading to increased interactions and collisions between galaxies. These galactic mergers would be cataclysmic events, triggering bursts of star formation and altering the structure of galaxies significantly. Following the merger of galaxies, star systems would then start to collide and merge, disrupting planetary orbits and leading to widespread stellar chaos. The night sky on any remaining planets would appear vastly different, filled with a much denser array of stars, and the conditions on these worlds would become increasingly hostile to any form of life. In the final stages of the Big Crunch, the density and temperature of the universe would rise enormously as stars, planets, and eventually atoms are crushed together. This phase could mirror conditions similar to those in the early universe, but in reverse, culminating in a singularity where all the universe's matter and energy are compressed into an infinitely small point, potentially setting the stage for another Big Bang if the cyclic model of the universe holds true. The concept of a multiverse introduces a fascinating twist to discussions about our universe's fate, suggesting that our cosmos might be just one of an immense number of universes within a vast multiverse. Each universe within this potential multiverse could have its own laws of physics, initial conditions, and consequently, its own unique fate. This idea not only expands the scope of cosmological speculation, but also offers alternative possibilities that challenge our understanding of the cosmos. In a multiverse, the fate of any single universe, including our own, could be influenced by factors that are entirely absent in other universes. For instance, while our universe appears to be on a path toward eternal expansion, possibly leading to a heat death or a Big Rip scenario, other universes might have different balances of matter, and dark energy, leading to fates like the Big Crunch, or even scenarios beyond our current scientific imagination. One intriguing aspect of the multiverse theory is the idea of bubble universes, where each universe is like a bubble floating in a higher dimensional space. These bubbles might occasionally collide or be created through processes similar to cosmic inflation, suggesting that the birth and death of universes are events within a much larger cosmic context. Within this framework, the fate of any individual universe might be linked to interactions with other universes, or it could be determined by the specific conditions of its own inflationary history. The multiverse concept also allows for the possibility of universes with physical constants and laws dramatically different from our own. In some of these universes, the conditions might never allow for stars, galaxies, or life as we know it to form, while in others, entirely different forms of complexity and life could exist. This variability adds a rich layer of complexity to the question of a universe's fate, suggesting that there could be as many outcomes as there are universes in the multiverse. The bizarre and counterintuitive laws of quantum mechanics, which govern the behavior of particles at the smallest scales, may also have profound implications for the universe's ultimate fate. Quantum mechanics introduces concepts such as uncertainty, superposition, and entanglement, which seem to defy classical intuition. These principles, while primarily influential at microscopic levels, could play a critical role in understanding cosmic phenomena and the universe's eventual outcome. One area where quantum mechanics intersects with cosmology is in the realm of black holes. Stephen Hawking's prediction of Hawking radiation, a quantum mechanical process, suggests that black holes emit radiation and could eventually evaporate over astronomical timescales. This evaporation process could have significant implications for the universe's long-term evolution, particularly in scenarios like the heat death, where black holes become the primary remaining structures. As they evaporate, the energy released could be one of the last significant events in an aging universe. Quantum mechanics might also influence the fate of the universe through the concept of quantum fluctuations. These are temporary changes in the amount of energy in a point in space, as allowed by the Heisenberg uncertainty principle. In the very early universe, quantum fluctuations are believed to have been instrumental in seeding the formation of cosmic structures like galaxies and large-scale structures. Extrapolating this influence into the far future, it's conceivable that quantum fluctuations could lead to the creation of new particle formations or even new universes via mechanisms like false vacuum decay, where a more stable vacuum state is achieved through quantum transitions. This could drastically alter the universe's fate or even spawn new universes in a multiverse scenario. Furthermore, the principles of quantum mechanics challenge our understanding of time and causality, central components in any discussion about the universe's fate. Quantum entanglement, for example, suggests instantaneous connections between particles over any distance, defying classical ideas of cause and effect. This could imply a more interconnected cosmic fabric, where the fate of the universe is not merely a linear progression, but involves non-local phenomena that could either hasten or alter its end in ways not yet fully understood. Quantum cosmology, a field that attempts to apply quantum mechanics to the entire universe, offers possibilities like the quantum creation of universes from nothing, where quantum fluctuations in a pre-existing space or quantum vacuum could give birth to new universes. This opens up discussions about cyclic or bouncing universes, where the death of one universe could lead to the birth of another, potentially influencing the multiverse theory and our understanding of our own universe's place within a broader cosmic context. The possibility of unforeseen forces or phenomena that could significantly influence the universe's future remains a tantalizing and humbling prospect. Despite the incredible strides made in understanding the cosmos, from the laws of gravity that bind galaxies to the quantum mechanics governing subatomic particles, much about the universe remains mysterious and uncharted. The history of science is replete with moments where the discovery of new forces or phenomena radically altered our understanding, suggesting that the future of cosmological research may hold similar revelations. The dark sector, encompassing dark matter and dark energy, exemplifies the kind of unknowns that continue to challenge scientists. These entities constitute the majority of the universe's mass energy content, yet they interact with the observable universe in ways that are not fully understood. The discovery of either a new property of these dark components or an entirely new form of dark entity could drastically change our predictions for the universe's fate. Moreover, the theoretical framework of physics itself hints at the possibility of undiscovered forces. For example, the quest for a theory of everything, a unified framework that seamlessly incorporates quantum mechanics with general relativity, has led to propositions such as string theory and loop quantum gravity. These theories suggest the existence of additional dimensions and fundamental particles that could, in principle, mediate forces or phenomena not accounted for in our current models. Discoveries in this realm could introduce new dynamics to the cosmic evolution, potentially opening up pathways to understanding the universe's fate that we currently cannot fathom. Another avenue through which unknown forces could manifest is through the study of cosmic anomalies, observations that do not fit neatly into existing models. For instance, discrepancies in the observed velocities of galaxies within galaxy clusters and the outer stars in galaxies initially hinted at the presence of dark matter. Similar anomalies in the future could be the harbingers of new forces or constituents of the cosmos. The universe's very beginnings and the conditions that prevailed during the first fractions of a second after the Big Bang remain shrouded in mystery. Phenomena occurring at these energy scales, or in the earliest stages of cosmic inflation, could have left imprints that we have yet to interpret correctly or even detect. These relics from the universe's birth could hold the keys to understanding forces or phenomena that have shaped cosmic history and will determine its ultimate course. The idea that humanity could play a role in shaping the universe's destiny intertwines the realms of cosmology and human ingenuity, inviting speculation on a grand scale. While the vastness of the cosmos and the forces governing it dwarf human endeavors, the rapid advancement of technology and our deepening understanding of the universe prompt a reconsideration of the potential impact intelligent beings might have on cosmic scales. Humanity's ability to understand and manipulate the environment has transformed the Earth, and our ventures into space represent the first small steps toward influencing broader cosmic phenomena. Theoretical proposals, such as the Dyson sphere, a hypothetical megastructure designed to harness the power of a star, illustrate the potential for advanced civilizations to exploit stellar energy directly. While currently beyond our technological reach, such concepts hint at the potential for intelligent beings to significantly alter their local space environments. On a more speculative note, the pursuit of a unified theory of physics could unlock the ability to manipulate fundamental forces and particles in ways we can scarcely imagine. Achievements in this realm might one day allow for the stabilization of star systems, the engineering of black holes, or even the creation of artificial structures on cosmic scales. The potential to prevent local astronomical catastrophes, such as asteroid impacts, or to extend the lifespans of stars through advanced energy manipulation, could represent the first steps in an increasing capacity to shape cosmic events. The concept of directed panspermia, where life is intentionally spread to other planets or star systems by an intelligent civilization, could see humanity becoming a vector for the propagation of life throughout the galaxy. In this way, the human factor could influence the development of other worlds, potentially seeding new evolutionary paths or fostering conditions for the emergence of other intelligent species. The long-term survival and expansion of human civilization into the cosmos would require overcoming significant challenges, including those posed by the vast distances between stars, the hostile environments of space, and the need to create sustainable habitats beyond Earth. Achieving such feats would necessitate not only technological prowess, but also a profound commitment to collaboration and the stewardship of cosmic resources. While the impact of humanity on the universe's destiny may seem negligible in the face of its immense scale and forces, the potential for growth in our understanding and capabilities suggests that the role of intelligent life in the cosmos should not be underestimated. Whether through the direct manipulation of cosmic phenomena, the spread of life, or the pursuit of knowledge that reshapes our relationship with the universe, the human factor introduces a dynamic element to the cosmic narrative. The concept of entropy, a measure of disorder or randomness in a system, plays a pivotal role in predicting the end of the universe. According to the second law of thermodynamics, in any closed system, entropy tends to increase over time until it reaches a maximum. This fundamental principle of physics suggests that the universe, if considered as a closed system, is gradually moving towards a state of maximum entropy. This inevitable increase in entropy is often associated with the ultimate fate of the universe, leading to a scenario commonly referred to as entropy's victory. In a universe ruled by maximum entropy, all energy distributions would become perfectly even, and temperature differences would vanish. This uniformity means that no work can be extracted from any part of the universe because work relies on energy moving from areas of high concentration to low. In such a state, all processes that consume energy, such as life, stars shining, planets forming, or even black holes evaporating, would cease. The universe would reach a condition known as thermal equilibrium, where all points in space are at the same temperature, and no further changes occur. Visualizing a universe dominated by entropy evokes a picture of cosmic stillness and uniformity. The vibrant cosmos we observe today, with its galaxies, stars, and planets, would be replaced by a featureless expanse. Stars would have exhausted their nuclear fuel, galaxies would no longer form, and black holes, the last bastions of gravitational order, would have evaporated through the emission of Hawking radiation. What remains would be a dilute soup of particles and radiation, spread thinly across an ever-expanding space, with no gradients to drive movement or form structures. As the universe marches inexorably toward its final act, the last black holes stand as monuments to the cosmos's earlier, more turbulent epochs. These gravitational behemoths, the remnants of collapsed stars and the engines at the centers of galaxies, will undergo a slow but inevitable transformation that has profound implications for the universe's endgame. The key to understanding their fate lies in a process known as Hawking radiation, a theoretical prediction by physicist Stephen Hawking that black holes are not entirely black, but emit radiation due to quantum effects near their event horizons. Hawking radiation results from the creation of particle-antiparticle pairs in the vacuum near the black hole's event horizon. Occasionally, one particle falls into the black hole while the other escapes, leading to the black hole losing mass over time. This process is exceedingly slow for large black holes, taking many orders of magnitude longer than the current age of the universe to have a noticeable effect. However, as the universe ages and expands, these last black holes will become the primary actors on the cosmic stage, gradually evaporating away their mass in the form of Hawking radiation. The evaporation of the last black holes marks a significant milestone in the universe's journey toward maximum entropy and thermal equilibrium. As they emit Hawking radiation, they not only lose mass, but also release energy back into the universe. This energy, however, will be distributed in an increasingly sparse cosmos, contributing to the overall cooling and dilution of energy density in space. Once the last black hole evaporates, a process that could take up to 10 circumflex 100 years, a time frame far beyond human comprehension, the universe will be left without significant concentrations of mass or energy capable of forming new celestial bodies or driving cosmic phenomena. The significance of the last black hole's evaporation extends beyond their role as cosmic landmarks. It symbolizes the transition of the universe into a state where no large-scale structures exist, and all that remains are low-energy photons, electrons, neutrinos, and possibly dark matter particles, diffusely populating an ever-expanding space. This state represents the ultimate realization of entropy's victory, a universe where all available energy has been expended and no work can be performed. In the distant future, as the universe ages and evolves toward a state of maximum entropy, the conditions for life as we know it will become increasingly challenging. Theoretical speculations on survival in a degenerate universe, where stars have extinguished and black holes have evaporated, paint a picture of extreme adaptation and ingenuity. If any forms of life or consciousness are to survive into this far future, they would need to adapt to the harsh conditions of a dying universe in ways that stretch the limits of our current understanding of biology, physics, and engineering. In such a universe, traditional energy sources like sunlight or chemical reactions would be scarce or non-existent. One conceivable strategy for survival would involve tapping into the most fundamental and pervasive energy sources available. For example, civilizations might harness the energy of Hawking radiation emitted by evaporating black holes, though this would require technological advancements far beyond anything currently imaginable. Another speculative strategy might involve the direct conversion of mass into energy. As matter becomes increasingly diluted across the expanding universe, extracting usable energy from the sparse particles and radiation could be a way to sustain life. This could involve advanced forms of matter manipulation or even quantum-level energy extraction mechanisms, enabling the direct use of subatomic particles' energy. Survival in a degenerate universe might also necessitate radical changes to life forms themselves, possibly through bioengineering or the development of post-biological life. Life might take the form of highly efficient, low-energy entities capable of functioning in environments with minimal resources. These entities could be engineered to hibernate for extended periods. Awakening only when energy conditions are favorable, or they might exist in a state of reduced metabolic activity, extending their operational lifespans to eons. Furthermore, given the isolation imposed by the vast distances between remaining energy sources, any surviving entities would likely need to be highly autonomous, with the ability to repair, replicate, and evolve without external intervention. This could lead to forms of life or consciousness that are fundamentally different from anything we know, potentially based on entirely new substrates like quantum computing structures that can operate at minimal energy levels. Communication and travel would pose significant challenges in a degenerate universe, potentially leading surviving entities to develop highly advanced forms of information storage and transmission that can endure the long cosmic night. Information might become the primary currency of exchange, with knowledge preservation and transmission being vital for any form of society to persist. In a universe marching towards its ultimate fate, whether it be through heat death, the Big Rip, or another scenario, our understanding of time and causality, fundamental concepts that underpin our experience of reality, could be profoundly challenged and altered. Time's arrow, a metaphorical expression used to describe the one-way direction or asymmetry of time, is closely tied to the second law of thermodynamics, which posits that entropy within a closed system will not decrease over time. As the universe evolves toward a state of maximum entropy, the very fabric of time and causality might present nuances not accounted for in our current understanding. In the far future, as the universe approaches a state of thermal equilibrium in the heat-death scenario, the lack of distinguishable events could make the flow of time seem to stand still from a certain perspective. Without changes in energy states to mark the passage of time, entities within such a universe might not experience time in any meaningful way. This raises philosophical questions about the nature of time. Is it a fundamental part of the universe, or is it an emergent property dependent on the existence of change and causality? The concept of causality, the relationship between cause and effect, could also be re-examined in a universe nearing its end. Quantum mechanics already challenges classical notions of causality with phenomena like entanglement, where particles can instantaneously affect each other regardless of distance, seemingly defying the conventional flow of time. As we explore the universe's fate, we might find that the fabric of space-time and the rules that govern causality at cosmological scales introduce new paradoxes and possibilities that stretch beyond our current quantum mechanical understandings. Moreover, if speculative theories such as the cyclic model of the universe, where the universe undergoes an infinite series of expansions and contractions, or the existence of a multiverse hold true, our perception of time as a linear progression from a singular beginning towards a singular end may be overly simplistic. In such scenarios, time might be better conceptualized as a more complex, perhaps even multidimensional landscape, where causality operates in ways that are not immediately intuitive to our current way of thinking. These considerations suggest that as the universe evolves, the entities within it, assuming they can survive the harsh conditions of the far future, may develop entirely new frameworks for understanding and experiencing time and causality. These frameworks could account for the altered physical conditions of a maximally entropic universe, or incorporate insights from quantum mechanics and theoretical physics that challenge our current paradigms. Quantum fluctuations, the temporary changes in energy that occur in a seemingly empty vacuum, represent a cornerstone of quantum mechanics, revealing the inherent unpredictability and activity of the quantum vacuum. In the context of a dead universe, an expanse nearing or at maximum entropy, devoid of stars and galaxies and approaching absolute cold, these fluctuations might still occur. Intriguingly, some theoretical physicists speculate that under the right conditions, quantum fluctuations could give rise to new universes, suggesting a possible cyclical nature of cosmic events. In a universe that has reached its end state, where matter is dilute and energy is evenly distributed, the fabric of space-time might still experience these quantum fluctuations. These fluctuations could, in principle, lead to the formation of low-energy virtual particles, a phenomenon observed in the laboratory setting. Extending this concept, it's conceivable that under extremely rare and specific conditions, a quantum fluctuation could produce a localized concentration of energy dense enough to trigger a new Big Bang, birthing a new universe within the old one. This notion ties into the idea of the multiverse, where our universe is just one of potentially many universes, each with its own physical laws and constants, spawned from the quantum foam of the larger multiverse. Such a process would imply a cyclical, or at least an ongoing, nature of cosmic events, where the death of one universe sets the stage for the birth of another. The implications of such a scenario are profound, challenging our understanding of time, causality, and the very nature of existence. If quantum fluctuations can indeed spawn new universes, it suggests that the cosmos is eternally rejuvenating itself, with cycles of birth, evolution, and death, followed by rebirth. This cyclical model contrasts with the linear progression from the Big Bang to heat death traditionally envisioned in cosmology. The singularities within black holes, points of infinite density where the laws of physics as we know them break down, have long fascinated physicists and cosmologists. A tantalizing hypothesis proposes that these singularities might not merely mark the end of matter's journey within our universe, but could also serve as seeds for the birth of new universes. This idea suggests a profound connection between the end of one cosmic epoch and the beginning of another, weaving a tapestry of universe creation that links the life cycle of black holes to the genesis of entirely new cosmoses. At the heart of a black hole, matter collapses to a point of infinite density and zero volume, creating what is known as a singularity. The conditions at these singularities are beyond our current understanding of physics, potentially involving a union of general relativity, which describes gravity at the cosmic scale, and quantum mechanics, which explains the behavior of particles at the smallest scales. Some theories, such as the concept of quantum gravity, attempt to describe these conditions, suggesting that the extreme gravity of a singularity could rupture the fabric of space-time itself. This rupture could theoretically create a bridge or wormhole to another region of space-time, birthing a new universe that expands in its own dimension, separate from our own. The new universe would not necessarily inherit the physical laws or constants of its parent universe, allowing for the possibility of diverse cosmoses with vastly different properties and potential for complexity. The implications of black holes serving as seeds for new universes are profound. It challenges our understanding of causality, as the birth of a new universe from a black hole singularity would mean the end of one world is intrinsically linked to the beginning of another. This cyclical process could provide a mechanism for the multiverse, where each black hole in our universe has the potential to spawn a new universe, leading to an ever-growing ensemble of universes. This concept reshapes our perception of black holes from cosmic endpoints to gateways of cosmic rebirth. It suggests that within every black hole lies not just the end of certain paths in space-time, but the potential for entirely new beginnings. This perspective aligns with the broader view in modern cosmology that the universe is a dynamic, ever-evolving entity, with processes at both the grandest and most minute scales contributing to the cosmic life cycle. If the multiverse theory holds true, positing the existence of numerous universes beyond our own, each with potentially different physical laws and constants, it opens up profound questions about the nature of consciousness, information, and their persistence beyond the lifespan of a single universe. The intriguing possibility that consciousness or information might escape a dying universe and find refuge in another universe touches upon the intersections of cosmology, quantum mechanics, and theories of mind and information. The foundation of this speculative journey lies in understanding the mechanisms through which such a transfer could occur. One theoretical pathway involves quantum entanglement, a phenomenon where particles become interconnected in such a way that the state of one, no matter how far apart, instantly influences the state of the other. Extending this concept, some theorists suggest that if every bit of information in our universe, including the states that comprise consciousness, could be entangled with particles in another universe, then, in principle, the transfer of information might not be bound by the death of the parent universe. Another potential mechanism is through the singularities of black holes, theorized to possibly act as bridges or wormholes to other universes within the multiverse. If consciousness or information could be encoded in a form that survives the journey through such a singularity, this could represent another avenue for escape from a universe facing its demise. For consciousness itself to make such a leap, we would need a radical expansion of our understanding of consciousness as not just a product of brain activity, but as something that can exist independently of the biological substrate. This concept leans heavily into the realm of digital consciousness or mind uploading, where one's consciousness could be replicated on a non-biological platform capable of surviving the extreme conditions of inter-universal travel. However, each of these speculative pathways faces significant scientific and philosophical hurdles. Quantum entanglement, while experimentally verified, does not currently offer a means to transmit information in a way that could encompass consciousness. Similarly, the nature of singularities and wormholes, and their ability to connect to other universes, remains purely theoretical, constrained by our limited understanding of quantum gravity. The concept of transferring consciousness presumes that it can be fully understood and replicated outside of its biological context, a proposition that raises deep questions about the nature of identity, self, and continuity of experience. As the universe edges toward its ultimate fate, the principles of quantum mechanics and the conservation of information play pivotal roles in shaping theories about the universe's final moments and the possibility of a subsequent rebirth. The conservation of information, a principle deeply embedded in quantum theory, posits that information, defined in the broadest sense, encompassing all possible states of a system, cannot be destroyed, even if it can be transformed. This principle introduces profound implications for the universe's endgame and the notion of cyclicality or rebirth in cosmological models. At the heart of these discussions is the concept of black hole information paradox, which questions what happens to information that falls into a black hole. Stephen Hawking's revelation that black holes emit radiation, Hawking radiation, and can eventually evaporate, challenged the idea that information entering a black hole is forever lost. If black holes evaporate, leaving no trace, the question arises, where does the information go? The principle of information conservation suggests it must be preserved in some form, possibly encoded in the Hawking radiation itself. This debate has spurred deeper investigations into the nature of information at the quantum level and its implications for the universe. One theory posits that the universe's end could see all of its information encoded on a two-dimensional surface at its boundary, adhering to the holographic principle, which suggests that the entirety of a volume of space can be described by the information on its boundary. This model could imply that as the universe approaches its demise, all the information about its history, structure, and contents, perhaps even the seeds of consciousness or life, could be conserved on this cosmic boundary. This preserved information could, theoretically, provide the blueprint for a rebirth or regeneration of the cosmos. If the universe undergoes a cyclical process, such as in models that propose a series of big bangs and big crunches, the information preserved at the end of one cosmic cycle could influence the initial conditions of the next. In such a scenario, the universe's rebirth would not be a tabula rasa, but would carry imprints or echoes from its previous incarnation, guided by the fundamental laws of quantum mechanics and information conservation. Advancements in understanding quantum gravity, a theory that seeks to reconcile general relativity with quantum mechanics, could reveal mechanisms by which information conserved at the universe's demise influences the fabric of space-time itself, potentially seeding the geometry and matter distribution of a new universe. This suggests a cosmos where end and beginning are intrinsically linked, bound by the immutable conservation of information. Humanity's understanding and contemplation of the universe's end offer profound lessons about our place in the cosmos and our approach to existential questions, grounding us in a perspective that is both humbling and inspiring. As we peer into the vastness of the universe and ponder its ultimate fate, we are reminded of our infinitesimal scale in both space and time. Yet, paradoxically, this realization does not diminish us. Rather, it elevates our appreciation for the complexity and beauty of the cosmos and our unique capacity to comprehend it. This cosmic perspective teaches us about the fleeting nature of existence, not just on a personal or species level, but on the scale of stars, galaxies, and the universe itself. It instills in us a sense of cosmic humility, acknowledging that we are part of a much larger and older process that extends far beyond our immediate concerns and lifespans. This realization can shift our existential questions from a human-centered narrative to a broader, more inclusive understanding of our place within the cosmic web of life and matter. Moreover, contemplating the universe's end and the principles governing it, such as entropy, the conservation of information, and the possibility of cyclical universes, challenges us to think deeply about the nature of time, causality, and existence itself. These concepts push the boundaries of human thought, inviting us to consider the possibility that our universe may be one of many, that our existence is part of a larger cosmic cycle, and that the legacy of humanity, and life as we know it, may be encoded in the very fabric of the cosmos. The exploration of these ideas also has practical implications for how we approach our lives and stewardship of our planet. Recognizing the rarity and preciousness of life in the context of the cosmos can inspire a greater sense of responsibility to preserve and cherish the delicate conditions that allow life to flourish on Earth. It can motivate us to pursue sustainable living, interstellar exploration, and the preservation of knowledge, culture, and biodiversity for future generations. The awareness of the universe's eventual end serves as a powerful motivator for human creativity, philosophical reflection, and the urgency to find meaning in our existence. This profound realization that the cosmos itself is not eternal and immutable but subject to decay and transformation touches the very core of our understanding of life, purpose, and the nature of existence. It compels us to confront the finiteness of everything we know and challenges us to derive meaning and purpose within these boundaries. In terms of creativity, the contemplation of the universe's demise has inspired countless works of art, literature, and music, as well as innovations in science and technology. Artists and thinkers have long grappled with the themes of impermanence and the end of time, using these concepts as a backdrop against which the drama of life unfolds. The vastness and mystery of the cosmos, juxtaposed with its eventual end, serve as a muse for exploring the depths of human emotion, the resilience of the spirit, and the boundless capacity for imagination. This awareness drives scientists and innovators to reach beyond our current limits, to explore the cosmos, to understand the fundamental laws of nature, and to ponder our potential to transcend our earthly origins and perhaps even the lifespan of our universe. Philosophically, the end of the universe invites a re-examination of existential questions and the values that guide our lives. It prompts inquiries into the nature of value, ethics, and our responsibilities to ourselves, each other, and the continuity of consciousness and culture. The finiteness of the cosmos can lead to a deeper appreciation for the moment, a greater investment in the legacy we leave behind, and a more profound understanding of the interconnectedness of all things. This perspective encourages a philosophy of stewardship, where the emphasis is placed on nurturing life, knowledge, and beauty, despite, or perhaps because of, their transient nature. The urgency to find meaning in our existence is perhaps the most direct impact of contemplating the universe's end. Faced with the ultimate impermanence of all things, individuals are driven to seek purpose in their actions and relationships, to create and share beauty, and to leave a lasting impact on the world and people around them. This awareness can inspire a shift from seeking external validation to cultivating inner richness, from accumulating material wealth to enriching the world with contributions that may ripple through time. In contemplating the preservation of knowledge for eons, humanity stands on the brink of an endeavor that stretches the imagination to its limits. This mission, aimed at passing on the legacy of our knowledge and existence to possible future civilizations or intelligences, requires innovative methods and messages that can withstand the ravages of time and the uncertainties of cosmic events. The challenge lies not only in preserving the information, but also in ensuring it can be understood by entities with potentially vastly different perceptions, languages, and technological capabilities. One approach to this monumental task is the creation of durable time capsules or monuments designed to last for millions or even billions of years. These could take the form of plaques or sculptures made from materials resistant to erosion, corrosion, and cosmic radiation, such as platinum or silicon carbide. The Voyager Golden Records, currently hurtling through space aboard the Voyager spacecraft, serve as an early example, containing sounds, music, and images selected to portray the diversity of life and culture on Earth. Another method involves encoding knowledge in the structure of DNA, taking advantage of its longevity and compactness as a storage medium. Scientists have already made strides in storing digital data in DNA, a technique that could be expanded to archive vast amounts of information about human history, culture, science, and technology. This DNA could be encapsulated in protective shells and placed in multiple locations on Earth and beyond, in the hope that future beings, whether they are descendants of humanity or extraterrestrial intelligences, might decipher it. The messages we choose to preserve must be crafted with universal principles and concepts in mind, aiming for a level of communication that transcends human language and cultural specifics. This might include mathematical sequences, physical constants, or simple pictograms depicting fundamental aspects of human anatomy, the Earth's location relative to known celestial objects, and basic concepts of chemistry and biology. The Arecibo message, sent into space in 1974, exemplifies this approach, using binary code to convey basic information about humanity and the solar system. Beyond physical methods, humanity could also consider more speculative strategies, such as attempting to send information through time via quantum entanglement or other phenomena at the edges of our understanding of physics. While such ideas venture into the realm of science fiction, they reflect the creative breadth of thought being applied to the challenge of intertemporal communication. Additionally, fostering a culture of preservation and continuity within human civilization itself can serve as a method of knowledge preservation. This could involve the continuous updating and safeguarding of repositories of knowledge, dedicated institutions or digital archives designed to survive global catastrophes and to be accessible to future generations. These repositories would not only store information, but also instructions on interpreting the data, possibly including keys to understanding human languages and technologies. As humanity gains a deeper understanding of the universe and our place within it, The awareness of its eventual fate brings to the forefront a range of ethical considerations of cosmic scale. These considerations compel us to reflect on how we engage with the cosmos, the responsibilities we hold toward future generations, and how we should interact with potential extraterrestrial life. Our actions, driven by the knowledge of the universe's vastness and its ultimate demise, carry implications that stretch far beyond our immediate concerns, touching upon the very essence of our legacy and stewardship of the cosmic environment. Firstly, the ethical engagement with the universe necessitates a profound respect for the cosmos as the broader context of our existence. This respect manifests in the commitment to cosmic preservation and the avoidance of activities that could have adverse effects on the celestial environment. As we venture into space, the principles of non-contamination and the preservation of celestial bodies in their natural states become paramount. These principles not only safeguard the scientific integrity of these environments for future study, but also honor the intrinsic value of the cosmos beyond human utility. Secondly, our understanding of the universe's fate deepens our responsibility toward future generations. This responsibility entails ensuring that succeeding generations inherit a wealth of knowledge and a culture of curiosity and exploration. It also involves the development and preservation of technology and information that could enable humanity to navigate the challenges of a changing universe, potentially including the search for new habitats beyond Earth. The ethical imperative to invest in long-term sustainability and interstellar exploration becomes a testament to our dedication to the continuity of human and terrestrial life. Furthermore, the prospect of encountering extraterrestrial life forms introduces complex ethical dilemmas regarding communication, coexistence, and the exchange of knowledge. The principles of mutual respect, non-interference, and the peaceful sharing of resources and information should guide our interactions. Recognizing the rights and autonomy of other intelligent beings and engaging with them in a manner that fosters mutual understanding and respect underscores our commitment to ethical conduct not only on Earth but in the cosmic arena. Back into how we actually find answers. We have powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope serve as humanity's eyes into the cosmos, allowing us to peer back in time and unravel the mysteries of the universe's evolution and potential fate. These cosmic telescopes harness advanced technology to observe the universe across various wavelengths, from visible light to infrared, revealing phenomena that remain hidden to the naked eye and providing crucial insights into the cosmos's past, present, and future. The Hubble Space Telescope, launched in 1990, has been a cornerstone in our quest to understand the universe. It operates primarily in the near-ultraviolet, visible, and near-infrared spectra. One of its most significant contributions is the Hubble Deep Field images, which showcased the vastness of the universe by revealing thousands of galaxies in a patch of sky previously thought to be empty. These observations have helped astronomers estimate the universe's age more accurately, understand the rate of its expansion, and discover the presence of dark energy, a mysterious force that is accelerating the universe's expansion. The James Webb Space Telescope, launched in December 2021, builds upon Hubble's legacy with its focus on infrared astronomy. The JWST can observe the universe at wavelengths longer than what Hubble can see, allowing it to peer through cosmic dust clouds and observe the light from the first galaxies that formed after the Big Bang. This capability is crucial for studying the early universe, understanding the formation and evolution of galaxies, stars, and planetary systems, and investigating the potential for life on planets orbiting distant stars. Both telescopes contribute to our understanding of the universe's fate in several ways. By measuring the rate of cosmic expansion and gathering data on dark energy, they provide insights into how the universe might continue to evolve. Observations of distant supernovae, for instance, have led to the conclusion that the universe's expansion is accelerating, a discovery that has profound implications for theories about the cosmos's ultimate fate. These telescopes help astronomers study the life cycle of stars, from their birth in nebulae to their death throes in supernova or as black holes. Understanding these processes is vital for piecing together the universe's large-scale structure and its chemical composition over time. Observations of phenomena like galaxy collisions and star formations offer clues about the dynamic processes shaping the universe and hint at how these might play out in the eons to come. The quest to detect dark matter, the mysterious substance that makes up about 27% of the universe but does not emit, absorb, or reflect light, has spurred a range of cutting-edge experiments. These experiments aim to unveil the nature of dark matter, which, despite its invisibility, exerts a gravitational pull on galaxies and clusters, influencing the cosmos's structure and evolution. Scientists have devised innovative methods to detect dark matter directly or indirectly, employing detectors buried deep underground, satellites in space, and large colliders that attempt to recreate the conditions of the early universe. One of the forefront experiments in the search for dark matter is the use of cryogenic detectors, such as those employed by the Cryogenic Dark Matter Search and the Xenon Dark Matter Project. Xenon. These experiments operate in deep underground facilities, such as the one located beneath the Gran Sasso Mountain in Italy, or in the Sudan Mine in Minnesota, USA, to shield them from cosmic rays and other background radiation that could obscure the signals they seek. The detectors are cooled to extremely low temperatures to reduce noise from thermal vibrations, increasing the chances of detecting the faint interactions between dark matter particles and ordinary matter. The Large Hadron Collider at CERN also plays a pivotal role in the hunt for dark matter. While the LHC is best known for its discovery of the Higgs boson, it also conducts experiments that could reveal dark matter particles. The collisions of protons at near light speeds have the potential to create dark matter particles under the right conditions. By analyzing the byproducts of these collisions, scientists hope to infer the presence of dark matter through missing energy and momentum that would suggest it was carried away by particles that cannot be detected directly. Another innovative approach is the use of space-based telescopes and observatories, such as the Fermi Gamma Ray Space Telescope, which searches for indirect signs of dark matter through the gamma rays that could be produced when dark matter particles annihilate or decay. By mapping the gamma ray sky, scientists can identify excesses of gamma rays from regions known to have high concentrations of dark matter, such as the center of our galaxy or nearby dwarf galaxies. Additionally, experiments like the Alpha Magnetic Spectrometer mounted on the International Space Station aim to detect dark matter indirectly by measuring cosmic rays. The AMS searches for anomalies in the flux of cosmic rays that could indicate the presence of dark matter particles decaying or annihilating into ordinary particles. The coming era of space exploration and astronomical observation promises to deepen our understanding of the cosmos through a series of ambitious missions and telescopes. These ventures aim to probe the dark corners of the universe, shedding light on the mysterious forces of dark matter and dark energy, unraveling the early universe's secrets, and perhaps, most intriguingly, uncovering the fate that awaits the cosmos. At the forefront of this endeavor is the James Webb Space Telescope, which, following its successful deployment, is set to continue peering into the universe's depths. Its infrared capabilities allow it to look back in time to the universe's infancy, offering clues that could illuminate dark energy's enigmatic nature. Similarly, the European Space Agency's Euclid mission is gearing up to map the dark universe's geometry, seeking to understand how dark matter and dark energy influence the universe's evolution and eventual fate. The Nancy Grace Roman Space Telescope, a NASA initiative, promises to explore the cosmos with an unprecedented breadth, focusing on dark energy, dark matter, and the properties of exoplanets. Its wide-field view will capture the cosmos in detail, far surpassing current capabilities, potentially revolutionizing our understanding of the universe's expansion and the forces at play within it. Ground-based projects like the Square Kilometre Array, SKA, and the Vera C. Rubin Observatory will complement space-based missions by providing detailed radio observations and conducting the Legacy Survey of Space and Time, LSST, respectively. The SKA's vast radio telescope network will delve into the universe's early days, exploring cosmic magnetism and gravity, while the Rubin Observatory's LSST will offer a comprehensive survey of the cosmos, uncovering faint objects and phenomena that could hold the keys to understanding dark matter and dark energy. The Laser Interferometer Space Antenna, LISA, an ESA mission with NASA contributions, plans to open a new window on the universe by detecting gravitational waves from space. This could provide unprecedented insights into the merger of supermassive black holes and test our theories of gravity, potentially revealing new aspects of the universe's structure and destiny. Additionally, the Dark Energy Spectroscopic Instrument, DESI on the ground, seeks to measure dark energy's effect on the universe's expansion. By creating a detailed 3D map of the cosmos and studying millions of galaxies and quasars, DESI aims to shed light on how the universe's acceleration is influenced by dark energy. Together, these missions and observatories are poised to revolutionize our understanding of the cosmos. By mapping the universe with unparalleled precision and depth, they aim to answer fundamental questions about its structure, origins, and fate. As these projects progress, they will not only extend the boundaries of human knowledge, but also challenge our understanding of the universe, potentially uncovering new physics that could explain the ultimate destiny of the cosmos. Reflecting on the vastness of time and the universe's potential end without succumbing to fear is a profound challenge that touches on the essence of our existence and our understanding of our place in the cosmos. This contemplation requires a shift in perspective, from viewing the end as a source of fear to seeing it as a natural part of the cosmic cycle and an invitation to find meaning and purpose in the time we have. One approach to facing the universe's vast timelines and eventual demise without fear is to embrace the concept of cosmic humility. Recognizing our small place in the grand scheme of things can be liberating rather than frightening. It underscores the interconnectedness of all things and the privilege of being a part of something so vast and complex. This humility encourages us to appreciate the beauty and wonder of the universe, fostering a sense of awe and curiosity rather than dread. Another way to approach the contemplation of the universe's fate is through the lens of legacy and contribution. Rather than focusing on the end, we can concentrate on what we can do now, how we can contribute to the knowledge, beauty, and well-being of our world and those who may come after us. This perspective shifts the emphasis from the fear of the end to the motivation to make a positive impact, encouraging us to live our lives in a way that adds to the collective story of humanity and the cosmos. Philosophical and spiritual traditions across cultures offer insights on contemplating impermanence with equanimity. Many teach the value of living in the present, embracing change as an inherent aspect of existence, and finding peace in the continuity of the cosmic cycle. These teachings can provide comfort and guidance in facing the vastness of cosmic time, suggesting that endings are also beginnings, and that the cycle of creation and dissolution is a fundamental aspect of the universe. Engaging with the scientific exploration of the cosmos can also transform fear into fascination. Learning about the universe's mysteries, the forces that shape it, and our place within it, can fill us with wonder and a desire to learn more, rather than fear of the unknown. This quest for understanding can be an enriching endeavor that connects us more deeply to the cosmos and to each other. The unknown future of the universe enriches our appreciation for the wonder of the present moment. By recognizing that the cosmos is in a state of constant flux, we are reminded to cherish the beauty and intricacy of the universe as it exists now. The knowledge that stars are born and die, that galaxies collide and reform, and that the universe itself is expanding at an accelerating rate, lends a sense of urgency to our quest to explore and understand as much as we can, while we can. This quest for understanding also fosters a profound sense of connection. In exploring the cosmos, we are reminded of our shared origins in the stardust of ancient stars. This cosmic perspective fosters a sense of unity and purpose, motivating us to overcome terrestrial divides and collaborate in our exploration of the universe. The unknown future of the cosmos thus serves as a call to collective action, a reminder that together we can push the boundaries of what is known and venture into the unexplored. The contemplation of the universe's eventual end evokes a spectrum of reactions, from existential dread to philosophical acceptance. However, the question of whether we should be concerned about the universe ending requires a nuanced understanding of cosmic timescales and our place within the cosmos. Firstly, it's essential to recognize that the universe's potential ends, whether through heat death, the Big Rip, or another scenario, are billions, if not trillions of years away. These timescales are so vast that they dwarf the span of human history and even the age of the Earth itself. In this context, the immediate concerns of humanity, such as addressing climate change, preserving biodiversity, and ensuring the well-being of current and future generations, take precedence. These are the issues where our efforts can have a meaningful impact. Moreover, the study of the universe's fate is not just an exercise in curiosity, but a testament to the human spirit's reach and ambition. Our desire to understand the cosmos, its origins and eventual outcomes, speaks to our profound need to find our place within the grand tapestry of existence. This pursuit of knowledge enriches our culture and philosophy, offering perspectives that can help us navigate our own lives with greater wisdom and compassion. While the end of the universe might seem a distant abstraction, it also serves as a reminder of the value of the present and the importance of stewardship. Knowing that stars will one day cease to shine and galaxies will drift apart underscores the preciousness of the cosmos's current state, with its abundant life and beauty. It encourages us to cherish and protect our tiny corner of the universe, our planet, and to strive for a legacy that transcends our brief moment in cosmic history. Additionally, the inevitability of the universe's end can inspire a sense of cosmic humility and collective purpose. It highlights the shared destiny of all inhabitants of the cosmos, suggesting that our differences are trivial compared to our common origins and fate. This perspective can foster a sense of unity and cooperation, motivating us to work together to solve the pressing challenges we face. As we come to the end of our journey through the cosmos, we've delved into the mysteries of the universe, exploring concepts like dark matter, black holes, and the ultimate fate of the cosmos. From the birth of stars to the potential rebirth of entire universes, we've grappled with questions that have intrigued humanity for hundreds of years. Through our exploration, we've glimpsed the vastness of space and time, gaining insights into the workings of the cosmos and our place within it. We've marveled at the wonders of the universe and pondered the implications of its eventual end. Along the way, we've been reminded of the importance of scientific inquiry, curiosity, and imagination in our quest to understand the cosmos. How do you think the universe will end? Will it end in a bang, or will it never even end in the first place? Let us know your thoughts below and subscribe to our channel for more documentaries like this one. Thanks for watching.